application of vectors navigation. So we've got an airplane. It's flying toward the northeast at 300 miles per hour. Let's draw that here as a vector. This means here's what's programmed into the plane. Okay, the plane is being aimed in a northeast direction at 300 miles per hour. This angle would be 45 degrees. But the thing is, there's a wind, a north wind. That means a wind coming from the north, so heading toward the south. And the wind is going to have an impact on the airplane. So the instrumentation in the plane is pointing the plane in one direction, but the wind is going to impact both the speed and the final direction the plane travels. Now I want to mark the wind on here as a vector as well, and I'll draw it where the first vector left off. So right here, I'm going to start it. It's heading toward the south, and it has a length of 40 for the 40 mile per hour wind. Let's call the airplane vector, vector A, and the wind vector, vector W. I want to know, yeah, but what's going to actually happen to this plane? The speed is going to be impacted by the wind. We call that the ground speed. And the bearing of the plane, the direction, is also going to be impacted by the wind. Remember that bearing is measured from north, going in a clockwise direction. Well, the answers to both of those questions can be found by considering the resultant vector, which I can draw on right now. I've already set my two vectors up in the tip to tail format. Here is vector r, the resultant vector. The direction of vector r, that's where the plane is actually going to go. You can see that the wind is pushing the plane off course a little bit. The speed of the plane relative to the ground is also being impacted. It looks to me like the wind is slowing the plane down a little bit. Well, let's start answering the questions. The ground speed of the plane would just be the length of vector r. How can I find that? Well, I have a triangle. It's an oblique triangle, so I'll have to make use of the law of sines or the law of cosines. What do I know? I can see two of the sides. Do you see that we also know this angle right here? It's all about geometry. Here is the y-axis. Vector W is parallel to it. Vector A is a transversal that cuts across, which means this angle here must also be 45 degrees. We're getting that from geometry. Well, that's great, because then I have an SAS situation in this triangle, and I can find the length of vector r. I'll call that length c to match the law of cosines, but I have c squared is equal to 300 squared, 40 squared, minus 2 times 300 times 40 times the cosine of the angle in between, which we've just written down to be 45 degrees. I can square root each side and then take that to the calculator, and what I have will be the length that I'm interested in. So I have the square root of 300 squared plus 40 squared minus 2 times 300 times 40 times cosine of that angle in between, which was 45 degrees. Close off all my parentheses, and that comes out to be 273.2. Well, that's the answer to the first question. The ground speed of the plane, because of that wind, turns out to be 273.2 miles per hour. Okay, the next question is, what's the final bearing of the plane? The programming in the plane told it to go on a bearing of 45 degrees, right, this angle. But the wind is pushing the plane so that the final bearing is a little bit bigger than that. It would be this angle right here. How am I going to find that? Well, I think what I can do is I can find this tiny angle of the triangle and then add that on to the 45 degrees. Now that angle is opposite side 40, which I was calling B, so that would make this little thing angle beta. And I have enough information in this triangle that I can use the law of sines now in order to find angle beta. I can see that angle beta is an acute angle. What pair do I know? Let's see. I know the 45 degree and 273.2 pair. So that would be sine of 45 degrees divided by its opposite side, the 273.2. Now that is a rounded number. I'm going to remind myself of that. Equals sine beta divided by b, which was 40. Cross multiplying is going to give me 273.2 sine beta equals 40 sine 45. So sine beta is 40 sine 45 divided by that 273 number. And all I would have to do to get beta is the inverse sine of that ratio. So in the calculator, I'll type sine inverse. On the top, I have 40 sine 45. And then on the bottom, I have that 273 number, which I'll come up and grab there to make sure I use the full answer. Close that parentheses, and I think we've got it. Comes out to be about 5.9 degrees. Now, that is not the final answer to the question. Bearing, remember, is measured from due north, going around clockwise. This bearing was 45. We're now adding on that tiny little extra bit of 5.9 degrees. So adding that on to the 45 would leave me with a final bearing of 50.9 degrees. The final part of this problem asks us to write down vector r, the resultant vector, in its component form. That means I need to know how long this is, the horizontal component, and how long this is, the vertical component. If I hadn't already done all this work, then I would probably take advantage of the fact that vector r is equal to vector a plus vector w. I would find the component form of vector a, which should be pretty easy because it's part of a 45, 45, 90 triangle. And I would find the component form of vector w, which is even easier because it's just pointing straight down. And I would just add those two vectors together. But since we have done all this work already, it's probably faster to just work with this green triangle right here. I know this angle. I know that because it's what's left over from 90 degrees after you subtract out that bearing. You can see that, right? The sum of the 45 and the 5.9 and that third angle down there must be 90. So if I just subtract that angle from 90, I'll call it angle theta, I'm going to get 39.1 degrees. That's this angle right here. Well, I can easily use that then to find the missing legs of this right triangle. How about I call them r sub 1 and r sub 2? And again, this angle here is the 39.1 degrees. I can write some sine and cosine statements. Sine of 39.1 would be equal to the opposite, which is r sub 2, divided by the hypotenuse. We figured that out a while back, was 273.2. And cosine of 39.1 would just be adjacent over that same hypotenuse. And you can see if I just multiply both sides here by 273.2, I'll have the numbers that I want. R2 is 273.2 sine 39.1. R1 is 273.2 cosine 39.1. I can get those right off the calculator. I just need to calculate 273.2. Again, I'm going to grab the full version of that number, times sine of the 39.1 degree angle, again using the precise versions. That's one calculation that I needed. And then how about I just pull up that last entry. So I'll head on top of the sine, switch it to cosine, and there's the second calculation. So R2 appears to be 172.1 and R1 212.1. Those are the two numbers I needed. Therefore, here is vector r in component form. Thanks for watching.